Yeah, the title is a bit broad, but I'm really going to talk about segmented muscles in lots of different types of images. But there's also one point I want to make, and a good segue into that is this recent paper that some of you have written, and I hope everyone else as well, about what happened in SPM in the past and what's going to happen in the future. And the conclusion points in the discussion was that SPM doesn't embrace discriminated models, essentially. Right. And I'm going to try to convince you that some discriminated models are good and can be used, and it's a big job. Yeah, so dozens are inherently multi-scale. So if you're learning about the vascular anatomy, you're going to start at the level of the main arteries and veins. And then you're maybe going to focus on the head, where you have like this branching into some networks, and then the brain branches again. And you can go into the cortex and branches again, and all the way down to capillaries, which are about 2 micron scale. So obviously it can't be imaged at once, so we have lots of different imaging modalities that allow you to produce different scales of the vascular network. And there are two main families of methods when it comes to segmenting vessels. There's the old stuff and the new stuff. The old stuff is essentially using vessel-less filters that enhance structures that are thin and long. And the good thing is it's quite generic. It actually works okay. It's easy to tune. There's just like a couple of parameters that can be tweaked. The issue is quite sensitive to noise. So if your noise, if your nice to load, and it just doesn't work. And it's not like there's a off-the-shelf version that just works on anything. So you need to retune your parameters to each new modality and each new imaging scale. And it looks at quite local patches for so it's a really local thing. And now we can use more modern models that are trained on labeled data, which are really accurate, assuming that you have the right training data, pretty fast run at inference time, and they use much more global information, so they realize better. The issue is that you need labeled data, and for vasculature especially, it's quite hard to obtain. It's really painful to actually segment vessels. Don't do that. So there's a new family of method that uses machine learning, but with synthetic data, and that's what we're going to do. But first, let's just talk about segmentation in general, right? So segmentation is the point of, let's say I have an image, and what do I then know about the underlying anatomy that generates that image? And so the quantity we're interested in is the posterior about the anatomy given the image. And like, how do you define that quantity? Well, historically and in SPM world, we use a generative model. So we introduce additional variables that we know. If we knew those variables, so for example, the distribution of intensities in the gradient pattern, then we have a better idea of what the image is going to look like. And yeah, so introducing those additional latent things that are not observed helps us invert the model and recover the anatomy. And the way these things are fitted is usually, so kind of simplifying, it's all Bayesian based. You define a joint distribution. It has to be an analytical one, so you need to know the math behind that model. And then you define a parametric family of procedures. And then you need to maximize this ugly term, which is the elbow, so almost the log evidence. But what matters is that by maximizing this big ugly term, we actually minimize the distance between our posterior and so the parametric posterior that we work with and the true posterior of the model. But discriminating models are actually quite related, right? So instead of having an analytical joint distribution, you have something that you can sample from. You still have a parametric posterior, and usually we maximize this log likelihood under the posterior. But again, like if we look at what it means in practice, it means that we're finding the parametric posterior that's closest to the true posterior in the sense of that big distribution that we're sampling from. So like we start from the same point. We have a joint distribution on labels on anatomy and image, and we're minimizing a distance between the posterior and the true posterior. And they have advantages and drawbacks, whether you like model-based stuff and model-free stuff. The issue with generative models is it's hard to invert, and so we are restricted to quite simple forms of procedures. Whereas with discriminative models, you can just go crazy. But the issue is that in practice, our training data set is not infinity. So we have lots of issues with generalization and also overfitting them. But one way to kind of mix both is we just get rid of these big data sets. We start with a generative model, and we use that to sample form, and then just train our district model. And now we're back to minimizing the distance between this point procedure and the model-based procedure. So we're back into a world where we know what we're optimizing for. And it's what's underlying things like SynSeg and SITMorph, which are those modern methods for image segmentation and image registration, for example. And so we want to do the same but with vessels. And we need to have forward the generative model of vessels. There are very complicated ones, like this one. That's not what we're going to use, because we don't want to use something that's too realistic, because we then have the risk of not having a broad enough distribution. So we wanted quite weakly informative generative models. And so that's what we did. So we have this kind of model that just makes weird, fine, and weakly things. And we hypothesize that if we train a network to segment those things, it's going to work on proper vessels and proper images. So the first application is to optical coherence tomography, which is a really cool spectroscopy technique that has a really high throughput. So you can image quite large blocks of data at about 10 micron resolution. And yeah, so that's our generative model. We have a bunch of parameters on the distribution of the things that we generate. And then we make up also fake images, which are also governed by some hyperparameters. Train a model purely on the synthetic data, like the model has never seen any real data, and then apply it to some proper OCT data, which is what we have on the right. And we wanted to evaluate, like does it make sense what we're doing? So we compared it to training networks on real data and these real labels, but also on fake data generated from labels that have been more realistic than our wiki spaghettis. And in practice, so that's our results. So we're better, but I think what's really interesting is our worst performing, our worst score is actually quite high. Whereas if you look at networks training on real data, they do have like massive failure cases. So it's not like a perfect prediction, but it's like we never fail at all. Yeah. And so this is what the segmentation looks like. So we have two labels on the left and then the network segmentation on the right. And what you can see is there are actually like more fine processes in the network segmentation than in the manual labels. And when we focus on the data, most of these differences that would be false positives in theory are actually real vessels that the person labeling just missed because it's impossible to label so many vessels. Yeah, so it's quite a generative method. So we also applied it to ex vivo and more. And so these are whole hemisphere scans at about 120 micron resolution. And then we took a bunch of patches, got them labeled by two different persons that were really careful. And then we, again, trained the network with the same strategy, but just like tuning a bit the hyperparameters. And we can get much better dice than with our baseline. And something that's really close to actually the interrelated variability, right? So dice measures the overlap between the two labels and the predicted ones. And if you take your two labels and look at the overlap between the labels, actually only 60%. And now you get 53%. So it's quite good. And yeah, and so now that we've had this thing, we can apply it to the entire scan. And so what I'm showing is, so we're moving through the brain, and the vessels are, all of the vessels are present in a slab that's centered on that slice. So that's why they look like they're outside of the brain, but they're really just like in the next slice. And as far as I know, that kind of first vascular atlas in way at that resolution. So I think it's quite a bit of crucial that can do this. And I need to do it. Yes, with big requests. But yeah, so the strategy is quite generic. So we are extending it to more modalities. So we've seen ex vivo MR and the CT, but Chiara has also trained models for phase contrast tomography, for light sheet fluorescence microscopy, for time of flight imaging. And we're in the process of writing a paper on that. And the other thing that I wanted to mention is that, okay, so everything so far has been using purely synthetic data, but what if we do have some real data? Can we actually get better? And so we designed a learning strategy to try to optimize the synthesis procedure or the hyperparameters of the synthesis based on real data that's labeled. And so the nice points about that strategy, quite briefly, is that we're only introducing changes to the synthesis if they improve the accuracy on real data. So it's kind of like a two-step process. And thank everyone who was involved in the project and the funders. Happy to take questions.